Good morning, IB Math. How are you? So we're moving on now from the theory and the kind of the concepts behind the trigonometry to more of the applications. So today we're going to take a look at applications of the sinusoids and the transformations. We're going to kind of put it all together here. And my whole lesson today is 3 problems. Each of these problems are going to take a little bit of time to do. We'll need our calculator, so make sure you've got your calculator out and handy. We'll definitely be doing stuff on the calculators. All right, here we go. So for the first application, what I'm going to do is I'm going to give you a sinusoid. Now, the following sinusoid represents the average daily temperature in Fairbanks, Alaska. And I've got temperature as a function, and I'm going to put x, that's the day of the year, is 37 times the sine of 2 pi over 365 times x minus 101 plus 25. All right, so you can see all the transformations here from the last lesson. Let's just take a quick look at these transformations. The 37 is the amplitude, which means that it's going to go up as high as 37 and down as low as 37. Well, as high as above 37 and below 37 of what? Of the center line, 25. The center line is 25. So the temperatures in Fairbanks go as high as 37 above 25 and as low as 37 below 25. The period of sine, when the pattern repeats, is 2 pi over b, where b is how long it takes the pattern to repeat. If x is in days, a whole year is 365 days. Make sense? And then x minus 101, the phase shift. The sine wave, and sine starts at the middle going up, starts at day 101. That's when the temperature would be the average, or 25, the middle. All right, so what I'd like to do, I know that might be a little confusing. I want to go ahead and graph this. We're going to graph it, sketch a graph, and then we're going to answer some questions about the graph. All right, so I'm going to go to my y equals, and I'm going to type in 37 times the sine of, open another set of parentheses. I probably want to put this quotient in parentheses. So open parentheses, 2 pi divided by 365 days, close parentheses, times, open parentheses, x minus 101 days, close, plus 25. All right, now what would be a reasonable window for this? Well, if I think about the window, the x represents look at that window. That's a weird window. Why is that window? Oh, I'm in degree mode. What mode do I want to be in? I've got pi's here. I want to make sure I'm in radian mode. Oh yeah, we're about to graph a radian trig, so I want to make sure I'm in radian mode. All right, window. X represents the days, so I'm going to go from day 0 to day 365, which is 1 complete year, and we'll do 30 day increments, so about every month. Y's represent the temperatures. Now the lowest temperature, the center line is 25, it goes 37 below that. The lowest temperature is going to be negative 12. So I'm going to go from negative 20. The highest temperature will be center line 25 plus the amplitude, which would be 62. So I'm going to go to 70, scaled in 10 degree increments. Negative 20 to 70, scaled in 10 degree increments, 0 to 365 days, and graph it. Oh, I've got some scatter up here, haven't I? Do you see that? I must have been doing a problem where I had my scatter plots turned on. Let me turn those off, get that off the screen. There we go. I think I was doing something for one of my classes earlier this morning, or yesterday, last time I did graphing. All right, there we go. So here comes the temperature. This is the graph of temperature for 1 year, the average daily temperatures for 1 year in Fairbanks, Alaska. And there's no surprise that it's a sinusoid. The temperature here would represent day 0, which would be January 1st. Very cold. But it looks like it might even get a little bit colder. You know, January 10th, 11th might be the coldest. And then January, February, March, April, May, June, July, August, September, October, November, December. So remember, these tick marks are approximately every 30 days, so approximately every month. And you can see that in the winter months it's cold and the summer months it's hot. Now the 25 is the center line. If I go to my y equals and I graph the line 25, there it is right in the middle. So you can see that the graph, the center line is 25, its lowest point is 37 degrees below 25, and its highest point is 25 degrees above 35. The maximums and minimums, if I go to the graph again, 25 minus 37 is negative 12, that's going to be my minimum. 25 plus 37 is 30, 40, 50, 62, which will be my maximum. And if I graph them, you can see the line down at the bottom is the minimum, the line at the top is the maximum. So I can see that my center line is 25, it goes 37 above, 37 below. The next thing I noticed is that the period is 365 days, so that's one full cycle of, that's one complete period, one complete cycle of sine. And the phase shift of sine is 101. Well, what does that mean? All right, let me get off that. I'm going to delete the maximums and the minimums here for a minute, and I'm just going to leave the graph with the center line. We know that a sine wave, the sine wave, starts in the middle going up. So right here is where the sine wave starts. This sine wave has been pushed. The sine wave starts here going up and coming back down. This would be day 101. Day 101 is where the sine wave has been horizontally translated, moved that way, slided over. All right, so there, kind of everything in a nutshell. Now let's answer some questions about this. So, if you want to make a sketch of this in your notes, so you've got a sketch. But the questions I want to ask about this are, let's see. There's lots of questions we could ask. I could ask, on what day will a certain temperature occur? I could say, for example, what is the temperature on May 1st? What's the average daily temperature on May 1st? All right, so what I'm going to do to solve that is, let me get rid of that center line out there, so the only graph I've got is the nice well-behaved. On May 1st, I have to plug in x oh gosh, what day of the year is May 1st? Oh boy, here we go. So let's see. January has 31 days. February has 28. January, February, March, April. If I add all of those up, 8, 9, 10. Carry the 1, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be, May 1st would be day 121 of the year. I think it would. If I've done something wrong here, I don't care. Just evaluating is all I really care about. So let's find the average daily temperature on day 121. And I'm going to go to my calculate a value. It's going to ask for my x value. I'm going to plug in 121. And there it is. On 121, the average daily temperature that day was, it looks like 37.48 or 37.5 degrees. So the average temperature that day was a little bit above freezing. So I'm sure that it was freezing at night and maybe a little bit warmer during the day, but the average daily temperature was about 37.5 degrees on that day. I could also ask the question, when? When will the average daily temperature be at least 32 degrees? So when will the temperature be at least 32 degrees? Now to do that, in my y equals, I'm going to plug in 32 and graph it. And so this is 32. So these are my average daily temperatures getting warmer and warmer and warmer. What day is that right there? So I'm going to calculate intersection point of the two curves. G-solve intersect, Casio users, you're probably already done already. But for the rest of us, it looks like 112. So when x is 112, day 112, whatever day that is. If day 121 is in May, that's going to be at some point in April, mid to late April. The average daily temperature will finally be above freezing. So now in this example, notice in this example, I gave you, whoops, I've got stuff falling all over the place here. I gave you the sinusoid. That was given. And then all we had to do was graph it and analyze it and ask questions about it. What if I did not give you the sinusoid and you had to create it? So my next two examples are going to be two examples where we have to create the sinusoid. In the first example, we're going to another typical type of sinusoid where it's coming in, going out, getting higher, getting smaller, is tide. Is a tide problem. So now let's say that today the high tide occurs at 9:36 a.m. and the water is going to be 2.7 meters deep. Low tide will occur at 3:48 p.m. and the water will be 2.1 meters deep. Now what we're going to do, tide, ebb and flow of tide, is a sinusoidal function of time. The depth of the water as it comes in and goes out and comes in and goes out, it gets higher, goes lower, it gets higher and goes lower. It is a typical sinusoid. So what we're going to do is we're going to create a model of this sinusoid, and then we're going to look at answering some questions. All right, so first, the model. Now I know that high tide occurs at a certain time right there. So I have to think, am I going to be using sine or cosine? Well, time out here for a sec. Let's think about the two models. I've got sine wave and cosine wave. The sine wave starts at the center line going up. The cosine wave starts at the highest point going down. So if I'm taking, so think about this. A cosine wave starts at the highest point going down. Sine wave starts at the middle going up. All right. So if I've got high tide occurring at some time, this is going to be a cosine wave. I'm going to write everything here in cosine. Let's see what happens to my blue pens. Here we go. So I'm going to have y equals a cosine 2 pi over b x minus c plus d. There's the format. There's the format I need to plug everything into. So y equals, what's the amplitude going to be? Cosine times 2 pi over, what's the period? X minus, what's the phase shift? Plus d, what's the center line? So there's lots of watts and watts and watts in here. All right, so let's attack the amplitude and center line first, because I know that the high tide is 2.7 and low tide is 2.1. So what's halfway between them? If I add them together and divide by 2, I'm going to get, what is that? The amplitude is going to be 0.3, so 2.4. There's my center line. 2.4, and the amplitude is 0.3. It goes 0.3 above 2.4 and 0.3 below 2.4. So my center line is 2.4, and the tide is constantly going from 0.3 meters at a maximum above and 0.3 meters at a maximum below. There's my center line and my amplitude. What's the phase shift here? Cosine. Where does the cosine wave start? The cosine wave starts at 9:36 a.m. Well, I can't put 9:36 in here. I need to put it in as a decimal. How can I put 9:36 in as a decimal? Well, let's see. 9:36 is the same thing as 9 and 36 sixtieths. 9 and 36 sixtieths for the period is going to be, let's see, what would the period here be? I'm sorry, the phase shift here would be 9 and, well, let's just do this on the calculator. Here we go. 9 plus 36 sixtieths is 9.6. All right, so 9.6 is going to be my cosine phase shift. My cosine phase shift. So 9.6 is going to go in here. And then finally, what's my period? how long did it take to do a whole cycle? Well, from 9:36 to 3:48, it went from the highest to the lowest. How long did it take to go from the highest to the lowest? 9 to 3 is 6 hours and 12 minutes. Now, is that a full period, though? No. That went from the highest, the high tide, to low tide. If I want to go back to high tide, I have to add another 6 hours and 12 minutes. 12 hours and 24 minutes. I'm going to use the same trick that I did over here, is 12.4. So 12.4 is going to go under here. 12.4. All right, so now we have the model. Now we have the model. We created the model. And of course, once you've got the model, we're just answering a bunch of questions now about what's going on in this. So for example, well, let's go ahead and graph this and take a look at the tides. So go to my y equals, let's clear out the Alaska out of there. And I'm going to put 0.3 cosine, open parentheses, 2 pi divided by 12.4, close parentheses, open parentheses, x minus 9.6, close, close, plus 2.4. And my window, I'm going to have to change my window. Now, let's see, what does x represent? The time during the day. So let's go from 0 o'clock to 24 o'clock. 24 hours in a day. Y represents the tide. I'm going to go from 0 feet deep, 0 meters deep, all the way to 3 meters of depth. So from 0 to 3. So I'm going from 0 to 24 days, scaled in 1 hour. I'm 0 to 24 hours, scaled in 1 hour increments, and 3 to 70. What happened there? 0 to what did I say? 3 meters deep, scaled in 1 meter increments. Oh gosh, everything got messed up there. Let me double check this. So x is my day, hours. Go from 0 to 24 hours, scaled in 1 hour increments. Y is the depth of my water. Go from 0 to 3 meters, scaled in 1 meter increments. Okay, I think I got it. I'm going to hit graph now and take a look at it. Here we go. So here's the depth of the water as a function of time. Now, I noticed the high tide occurred at 9:36. That's going to be this point right here, 9:36. Let's ask some questions now. Given this model, suppose I ask the question, when did the first low tide occur? When was the first low tide? Well, I can see on my graph it's right there. I want to know that minimum right there. So Casio users, gsolve minimum, TI users, second trace, minimum, but I want that minimum over there. I have to drop my pins on either side of that minimum. So I'm going to go over here, drop a pin, go over there, drop a pin, hit enter again, and it looks like when x is 3.4-ish. So x is 3.4. Well, what time is that? Well, let's see. It's 3 o'clock and 0.4 of an hour. 0.4 times 60 minutes is 24. So 3:24 a.m. That's when the first low tide occurred. At 3:24 a.m. Now I could ask another question. How deep is the water at noon? All right, so how deep is the water? I want to evaluate this at 12. gsolve value, or second trace, which is calculate value, and I'm going to put in 12 here. Now notice, if I had said 1 p.m., we wouldn't put 1 in there. We would actually put 13 in there. 1 p.m. is 13. So how deep is the water? It looks like it is 2.5 meters deep at noon. And I could do, once I've got the model, you can do all sorts of things. It's really coming up with that model. That's the difficult part. That's the very frustrating part, coming up with the model. All right, so we've done the temperature in Fairbanks, Alaska. We've done a tide problem. Now the next classic problem, let's see, I'm going to clear everything out of here, get my calculator nice and ready for the next problem. The next classic type of sinusoid is a Ferris wheel. Suppose I have a Ferris wheel and I'm going to tell you a couple things about this Ferris wheel. For example, I'm going to tell you that the radius is 35 feet. The rider gets on at the base. This is where the rider gets on. And that is going to be 5 feet above the ground. So the rider gets on. When the rider gets on, they're 5 feet above the ground. The radius of the Ferris wheel is 35 feet. The other thing I'm going to tell you is the time it takes to do one revolution is 40 seconds. Now, believe it or not, that's all we need. We're going to use that information to create a model of this Ferris wheel. And then we can ask questions like, how high is the rider after 1 minute, or where is the rider, or when is the rider 10 feet for the 4th time, and all sorts of other questions about this. First question I want to ask myself is, am I going to use sine or cosine here? Okay, excuse me. Well, the rider's getting on at the lowest point and then going higher. So kind of time out here for a minute. Let's think about our two models. We had sine and cosine, and we know that sine starts at the center line going up, cosine starts at the maximum going down. What's going on in this Ferris wheel? In the Ferris wheel, we're starting at the lowest point and then going up. Well, neither one of those models seems to work. If I use transformations, negative sine, negative cosine, negative sine, take this and flip this upside down, starts at the center line going down. Negative cosine starts at the bottom going up. Now I think I see the model I'm going to use. Since on the Ferris wheel, we're starting at the lowest point and then going up. You can only go up from there. Starting at the lowest point and going up. This is going to be a negative cosine model. All right, here we go. So generically, I'm going to have y equals negative something, that's the amplitude, times the cosine of the period times x minus something plus something. Here we go, all the somethings again. My amplitude, how far above and below the center line do I go? The cosine, what's the period, and what's the phase shift of the cosine? All right, so let's start putting numbers in here. First, amplitude and center line. Well, the 35 degrees is the amplitude, isn't it? Because I've got a lowest point here and a highest point there. At my lowest point, I'm 35 feet below. My highest point, I'm 35 feet above. The amplitude is going to be 35 feet. What's the center line? Is it 35 feet? My center in the middle? No, because I'm starting 5 feet high. The center line is actually going to be 40. The lowest point I am on the ride is 5 feet high. The highest point I'm on the ride is going to be 35 plus 5, or in other words, 40 plus 35 would be 75 feet high. What's the period? Remember, the period is always 2 pi over b, and b is the period. Here it's going to be 40 seconds. So 2 pi over 40. What's the phase shift? In other words, the negative cosine starts at what time? At time equals 0, right? That's when the first part gets on the ride. That's a perfect cosine. The phase shift there is going to be 0. Gosh, that happened really fast. But here we have our model. All right, so let's go ahead and plug this in. Negative 35 times the cosine of, open parentheses, 2 pi divided by 40, close parentheses, open parentheses, x minus nothing, close, plus 40. And I know I don't need that minus 0 in there, and I could reduce this to pi over 20. Just like in the tide problem, I could have reduced that one to pi over 6.2 or something. And that's all. The cool thing about tides, I don't know if I said it, but the cool thing about tides is that's always going to be the period of every tide. So here we have our model. All right, so let's say that the ride is going to go, a complete ride goes for 4 revolutions. 4 times around is your ride. Then you have to get off, buy another ticket, get back on again. How long does it take to do 4 revolutions? Each revolution is 40 seconds. 4 times 40 is 160 seconds, just over 2 minutes. Why do we need that? Well, because we're going to graph this. So I'm going to go to my, there's my sinusoid. Now I'm going to go to the window. X represents time. I'm going to go from 0 seconds to 160 seconds, and maybe I'll scale it in, let's see, 40 seconds to go around once, 20 seconds to the halfway, 10 seconds. I'm going to scale it in 10-second increments. The Y's are the height. I'm going to go from 0 feet above the ground to, what's the highest point I'm going? 40 plus 35 is 75. I'm going to go to 80 feet above the ground, scaled in maybe 10-foot increments. Or let's go 5-foot increments. That way we can see where the bottom is. And graph. So here's my Ferris wheel over 160 seconds. I should get 4 complete rides. So here's where I got on. And notice that it's not quite 0. It's down there at 5 feet high. I go up and come down. That's 1 revolution. Go up, come down. 2nd revolution. Go up, go down. 2nd. Go up, go down. And there it is. 4 complete revolutions. So now we've got the model. We can answer all sorts of questions. For example, when is the rider, let's see, I'm going to just pick some random number here, 50 feet above the ground for the 3rd time. When is the rider 50 feet above the ground for the 3rd time? So 50 feet above the ground, I'm going to go to my y equals, I'm going to plug in 50 for y2 and graph it. There's 50 feet. So there they are, 50 feet above the ground going up, 50 feet of the ground going back down, 50 feet of the ground going back up, 50 feet coming back down. For the 3rd time, it's going to be that one right there. What time is that intersection? G-solve intersect, Casio users, and you're going to have to go over 3 times. TI users, 2nd trace, intersect, and I want to get my little cursor over there where the 3rd point, there it is. Drop the pins on either side, and it looks like when X is 51.8, so about 52 seconds after getting on the ride. About 52 seconds after getting on the ride, you are 50 feet high for the 3rd time, and it looks like you're going up. All right, so that's sinusoids. And the applications of sinusoids. It's tough. It's not easy. They can be very frustrating. Just reading them, interpreting them. Hopefully we've done some good examples here. Looking at the examples, take good notes. I know I went through them kind of quick. If you need to, pause the videos and go back. Make sure you got them all copied down in your notes. So now I want you to go ahead and do assignment 6-0. It's on page 417, and I want you to do 417 and 418. It goes over to the next page. I want you to do problems 1 through 4. Problem number 1 is going to ask you to create graphs of given sinusoids. We should be able to do that. It says you want to sketch them by hand, but practice doing them on the calculator. Number 2 gives you a sinusoid and then asks you a bunch of questions about it. You kind of have to rip it apart. Very similar to what we did with Fairbanks, Alaska. Number 3 asks you to create a sinusoid about this particular, tide. It's basically a tide problem, so very similar to the tide problem we did, just the numbers are going to be different. And then number 4 is a little bit more awkward. In number 4, you've got 6 different graphs, and you have to find the equations for the graphs. So take a look at them and decide, is it going to be a sine or a cosine? As a matter of fact, you're also going to see a tangent in there and maybe a cosecant or a secant in there. And you're going to have to try to work backwards to find the actual equation that goes with the graph. Number 4 is the one that's going to give you a hard time. If you were paying attention, did everything here in the notes, 1, 2, and 3 should be okay, but 4. And I want you to, for 4, I want you to try it, think what you can do, and then try graphing it and see if it's the same, and then look at the answer in the back of the book. And most of the time, when you see the answer in the back of the book, you'll be able to kind of backwards engineer it so that you'll be able to figure out, why does that equation go with that graph. All right, guys, good luck. Keep working out there, and I'll talk to you again soon. Bye.